So, okay, so what did we do last time? I think last time was a pretty important lecture. Do you agree? You learned to calculate derivatives, right? So, if I give you a function, a specific function, involving exponentials or polynomials, or some combination of them, you should be able by now to calculate the derivative, which is pretty cool. There's one type of derivative we haven't talked about yet, which is trigonometric derivatives. We will talk about them today, but first I would like to remind you of what we learned on Friday, because I think it was pretty important. I'm going to write it down again. So recall derivatives we learned a bunch of formulas. For example, we learned the power formula. Power formula means that the derivative of the function x to the n is n times x to the n minus 1. And this formula works for any real number n. Again, that's a symbol for the real numbers. You also have the exponential formula, if you will, which is that the derivative of the function e to the x is also e to the x, which is pretty cool. We also have what you might call the constant formula, or the derivative of a constant function. The derivative of that is just constant times the derivative of f of x. And we also have the sum formula, which says that the derivative of f plus g is the derivative of f plus the derivative of g. Okay, and we also have a couple of more advanced formulas, which was the product rule first, which says that the derivative of the product the derivative of the product can be written down as the individual derivatives. In this case, it's f of x times the derivative of g of x plus g of x times the derivative of f of x. And finally, we have the evil quotient rule. What is evil about it? Well, I don't like it because you can make mistakes by using it. So basically you should avoid it if you can, and if you have to use it, which I think we'll have to use it for the next couple of lectures even if we don't want to, it's g of x times the derivative of f minus f of x derivative of g of x divided by the function g squared. Okay. So I hope that's sufficiently clear that you can read this notation. So you should definitely learn these formulas. We're going to be using them the rest of the quarter. You should also try and remember to do your homework for these sections so that you can practice them. It's not enough to have seen them once. You have to have them in your hands, so to say. You should be able to use them without thinking too much about them, because you will always have something else to worry about. It won't, except for this next couple of lectures, it will never be just about calculating the derivative. You will need to do something with it, so you will already be worried about other things. So there's one thing we have not talked about before, which is trigonometric derivatives. But before that, I would like to point something out. The proofs of these things are not that hard. This we did in the case n equals 2, in the case n equals 1, in the case n equals 0. Case n equals 3, you could also do it by yourselves. The higher cases, you need a more complicated formula, but you can still look it up in the book, or maybe even come up with it yourselves. This we pretty much did, because we said that we calculated this in terms of the derivative at 0, and we said that the derivative of this function at 0 is 1. That's in fact how we defined the number e, was by saying that the derivative of this function at 0 was 1. This is simply a multiplication of a function, a rescaling of a function by c. If you stretch a function by c, this is what this formula says, the slopes are multiplied by c. They go higher. This is just follows from the limits. And I'm going to show you, this follows from the limit rules. And I'm going to show you the proof of this one now, which is actually not hard. So proof of the product rule. And it works as follows. The derivative of the product is equal to, by definition, the limit as h goes to 0 of a quotient. And that quotient is the function evaluated at x plus h, so f of x plus h, g of x plus h, minus f of x, g of x. But I'm going to do a trick. I'm going to add and subtract the same thing. And I'm going to add and subtract f of x plus h, g of x, that's a g, minus f of x plus h, g of x. And that's actually not a parenthesis. There you go. Okay, and then I subtract what I was supposed to subtract, which is f of x, g of x. Great. It's a little bit tight, but there you go. As you can see, the red, the two terms in the middle, I'm subtracting and adding the same thing. So this is not changing the limit. But by using that trick, I can write this down as two different limits. Okay, I'm going to break this down into two different terms. And one term is the function f of x plus h multiplied by g of x plus h minus g of x divided by h plus, and I'm going to write the next term in here, the limit when h tends to 0 of f of x plus h minus f of x, everything multiplied by g of x. Okay, let's think about what we did here. There's four terms here. So I broke it up into the first two terms by themselves. Actually, no, sorry. The first term and the third term by themselves. And the second term and the fourth term by themselves. Okay, so this is f of x plus h times g of x plus h minus f of x plus h times g of x. Okay, plus the limit of f of x plus h times g of x, which is here, minus f of x times g of x, which is down here. Okay, there you go. And of course, each of these things has a limit. What happens with what happens if you forget about this f of x plus h? What happens with this expression over here? G of x plus h minus g of x divided by h. Derivative of g, exactly. And when we multiply it by f of x plus h, we have something that's different. But remember, h is becoming closer and closer to 0. As h becomes closer and closer to 0, f of x plus h becomes closer and closer to f of x. That's right. So I can write this as f of x times the definition of the derivative, okay, plus, and now I can write what happens with this term in here. Well, this term in here does not even depend on h. I can take it out. So I can write this down as g of x multiplied by the derivative of f of x. And that's the end of the proof. Great. Questions? By the way, every time that I'm writing these rules, I'm actually not, I guess I should maybe write the fine print, but the full statement is something like, suppose that f and g are differentiable functions, right? Then f times g is also a differentiable function, and the derivative is this. But I am essentially assuming in this proof that the derivative of each of these functions exists. As you can see, I mean, this limit does not equal to this unless the derivative exists. So I'm implicitly assuming that each of these functions is differentiable. Am I assuming anything, for example, for the quotient rule? What do you think? We've done this before a few times. What am I assuming about the quotient rule?
The denominator cannot equal 0.
The bottom cannot be equal to 0. If the bottom is equal to 0, then this doesn't work. It's also a fine print. I believe that's all the fine print for this theorem. Okay, one could also do the derivative of the quotient rule. In fact, what I'm going to do is I'm going to defer that proof for a little bit, for a couple of lectures. As a matter of fact, you can always write, let me go back here for a moment. You can always write f of x divided by g of x. You can always write it as a product. Can anybody tell me how I can always write this quotient as a product? Yes, over here.
F of x times g of x to the negative 1 power.
That's right. So f of x times g of x to the minus 1. Okay, so you can know dividing by g is the same thing as multiplying by g to the minus 1. Right now, we would not know how to derivate that. But in a couple of lectures, and maybe even by Wednesday, you learn how to do that. So we can write this quotient as a product, and then we use the product rule that we just proved to prove the quotient rule. Okay, so let's do now an example. Well, actually we've already done a bunch of examples. We can do one more example, and then we move over to the trig derivatives. So for example, the derivative of, let's see, e to the x minus 7 x to the 4 plus 1 divided by x to the 3. Okay, it looks like a quotient rule, but by now you know better, right? So instead of using the evil quotient rule, we're going to rewrite this as e to the x times x to the minus 3. Okay, this is a parenthesis, minus 7x to the 4 minus 3 is just 1, plus 1x to the minus 3. Right? Great. And here we really only need to use the product rule once, because I have to use it here. Over here, this is easy and this is easy. I'm going to break that off from the first derivative. But let's think about the first derivative first. The derivative of e to the x times x to the minus 3. Well, that's equal to e to the x times the derivative of x to the minus 3, which is minus 3 x to the minus 2, or what?
4.
Minus 4, exactly. Minus 4 because it's minus 3 minus 1. Minus 3 minus 1 is minus 4. Plus the derivative of e to the x times x to the minus 3. Times the derivative of e to the x, which is e to the x also. So this whole thing minus the derivative of the second term, which is minus 7, plus the derivative of x to the minus 3, which once again is minus 3 x to the minus 4. And I'm gonna simplify this a little bit. This is let's see, minus 3 e to the x, x to the minus 4, plus e to the x, x to the minus 3, minus 3 x to the minus 4, minus 7. That's about as simple as it can be written. You can also factor out on e to the x, but it's not going to get much simpler than that. Okay, now let's talk about trig, not to confuse with trick or treat derivatives. Ha. Trig or treat, right?
That should be a shirt.
So, oh yeah, that should be a shirt, I hear from the front. So, let's see. We have the sine function, and we would like to know, this is going to be the sine of x function, and we would like to know what the derivative of that is. So before I tell you the answer, I would like you guys to guess it. No, let's guess it without actually knowing it. Let's look at the function first. So something like this, it goes down, and then it goes up again. Okay, so this is here, this is, what value is this? I think this is pi, right? Mm-hmm. And this is pi over 2, and this is 2 pi. Okay. Yeah, that's not a great looking sine function, but oh well. Make it a little nicer here. Okay, there you go. So still not very nice, but it works. Okay, so let's guess, or at least have a rough idea of the derivative function. I'm going to use this other pen, and I'm going to start making marks to mark what the derivative should look like. So for example, do we know, or do we have an idea what the derivative should look like around here at this point? No. At pi halves. Well, you can see that the function is flat, so the tangent is essentially has a slope of 0, so the derivative should go through this point. Similarly, at this location, 3 pi halves, the derivative should be 0. What about the derivative at 0? It's definitely not 0. It seems more like 1, right? You can see the slope is something like 1. Okay. So what about over here at pi?
-1.
It sounds like it's going to be the negative of that. And over here at 2 pi, it's once again 1. And over here, it's once again 0. So when you join the points, when you join the dots, you get this mysterious looking function. And you got to wonder, what function is that?
Oh my gosh, it's cosine.
That's right. So the mysterious derivative looks a lot like the cosine function. I'm going to give you one more evidence that that mysterious function is actually the cosine function. What evidence is that? It's going to be the derivative at 0. So the derivative of the function sine of x at the point x equals 0. Again, this notation looks very cumbersome, but think about what function we're talking about, and we're derivating where. So we're derivating the function sine of x, and we're derivating it at the point x equals 0. And this is equal to the limit when h tends to 0 of sine of x h plus 0 minus sine of 0 divided by h. But that is equal to the limit when h tends to 0 of sine of h minus 0, right? So I'm not going to write anything, divided by h. Okay, so let's think about what this means. The limit when h is really, really small angle of sine of h divided by h. So if you take a very, very small angle, I'm gonna write here essentially the unit circle, but only a tiny fraction of it. I'm going to write a small angle. Small angle, let's say alpha. Now what happens? In this class we're using radians. You may have noticed we don't talk about 360 degrees, we talk about pi and 2 pi. What does that mean again, radians? Well, radians means if you have a unit circle, let me just remind you. If you have a unit circle, how do you define an angle in radians? Does anybody want to remind me? Well, what is the length? What is the circumference of the whole circle? It's 2 pi, right? Unit circle, remember. So what is the length of this arc stretch from here to here? It's 1/4 of that, right? It's pi over 2. And what is the angle in radians? It's pi over 2, right? So as a matter of fact, in radians, the angle, what we call the angle in radians, is nothing other than the length of this piece of arc. Right? That's what we mean by radians. So in this case, in radians, the length of that little piece of arc is actually alpha. That's what we mean in radians by the angle, is the length of that arc. And what about the sine of alpha? Well, sine of alpha is just that vertical line. So that vertical line that goes straight down to 0 is sine of alpha, and the length of that arc that goes from 0 to that other line is also alpha in radians. As you can see, for small angles, those two lines are actually very, very similar. That's the punchline. Punchline is when alpha is very, very small, the arc alpha and the sine of alpha are very, very similar lines. One of them is a piece of circle, the other one's a straight line, but they look very, very similar. So sine of alpha is very, very similar to alpha. And what it means is that sine of alpha divided by alpha is very, very similar to 1. So what do you think that limit is? So the derivative, to go back, the derivative of sine of x at x equals 0 is equal to the limit when h tends to 0 of sine of h divided by h, and by the argument above, although I'm not actually proving it, but you can see I think it's pretty convincing evidence that this is actually equal to 1. Which is conveniently the cosine of 0. Okay, so that should be another further evidence that the derivative of sine is cosine. Okay, so at this point, without further ado, I'm just going to tell you that the derivative of the sine function is the cosine function. I know, shocking, right? So the derivative of sine of x is cosine of x. The derivative of the cosine function, and I haven't talked about that yet, but we will do in a moment, is actually minus sine of x. It's not sine of x, it's minus sine of x. And the derivative of the tangent function is actually equal to the secant squared of x. Now, those of you who have not taken trig in a while, what is secant again? The secant of x is 1 over the cosine. Okay, and just in case it shows up, although it might not today, the cosecant of x is equal to 1 over sine. And the cotangent is 1 over tangent. But that's just a reminder. This is officially new. Okay, and the proof of this result, the full proof, you can see it in the book. And basically, we don't have time to prove the whole thing, but I gave you a fair amount of evidence that the derivative of sine is cosine, and we're going to do the same thing with the cosine function. So let's draw the cosine function. The cosine function starts having value 1. It goes down to 0. And to minus 1, and then it goes up once more. Okay, so this value over here is, I believe, pi halves. This value is pi, 3 pi halves, and 2 pi. And this is minus pi halves. And now we're going to look at the derivative of the cosine function. So the derivative is flat, horizontal flat at 0. So we would expect that it has value 0 at 0. Over here, it seems to have a negative slope, so I'm going to write it as minus. Over here, we have a slope of 0, so the derivative should be something like 0. Over here, we also have a positive slope. Over here, it's 0 again, and so forth. Oh, sorry. Here. That's not a point, that's here. Okay, so when we join the points,
It's up there.
oh, wait a minute, up there, yes, you're right, sorry. When you join the points, you get this function. Which looks a lot like the sine function, but has a big difference. You see, the sine function goes up at 0. It does not go down at 0. So this function goes down at 0, and it looks a lot like the function minus sine of x. So minus sine of x. You should convince yourself, rather than just learning the formula, you should look at this thing and say, aha, it does look a lot like the minus sine function. Okay, so that's it. Now, what about the third one? What about the derivative of the tangent function? Well, that we're going to prove using what rule? Okay, so what rule is that?
Quotient.
Okay, unfortunately, we're going to have to use that quotient rule.
No.
So, and that, as we know, is cosine x squared on the bottom. And on the top, we have to write the derivative of the bottom, sorry, the bottom times the derivative of the top. See, now I'm getting confused. Cosine x times the derivative of sine x minus sine x times the derivative of cosine x, all divided by cosine x squared. And the derivative of sine of x by what we just did is cosine x. So this is cosine squared of x. And the derivative of cosine is minus sine over cosine x squared. And this is equal to cosine x squared plus sine x squared divided by cosine x squared. Now you guys all know cosine squared by sine squared, or sine squared by plus cosine squared, adds up to 1. So this is 1 over cosine squared, and this is the same as secant squared. That's it. Okay, now we can use this to prove derivatives involving sines and cosines. So for example, if you have something like, I don't know, e to the x cosine x minus 2x squared tangent x, and you want to derivate this, what is that? Well, once again, we're going to use the product rule in this case and the sum rule, or in this case more of a subtraction rule. And the derivative of this is e to the x times the derivative of cosine, which is minus sine of x, plus cosine of x times the derivative of e to the x, and then a minus 2x squared times the derivative of tangent x, and then plus or minus again?
Minus.
It's a minus. Why is it a minus? Because I'm derivating this thing, I'm splitting that derivative into a sum, so it's minus a sum inside of a parenthesis. When I get rid of the parenthesis, I get minus all over the place. And this is tangent of x times the derivative of 2x squared. Okay, and that thing is equal to minus e to the x sine of x, okay, plus e to the x cosine x minus 2x squared secant squared minus tangent x times the derivative of 2x squared. Now, once again, I would actually try to avoid, I would write, I was about to write something like tangent x times 4x. I think it would be better to write it as 4x tangent x. Why is that? If I write tangent x times 4x, it's not going to be clear whether it's tangent of the whole thing or just tangent of x and the whole thing multiplied by 4x. It's just a convenience. You can also write it as parentheses and you make big enough space and then times 4x. It works the same too. Okay, do you have any questions? Questions? No questions. Great. We're going to learn one more trick. with trig functions. And that is the following. So recall that the limit when, let's say, x goes to 0 of sine of x over x is equal to 1. That was originally presented as, some kind of auxiliary thing, some kind of technical result, but I would like to think about that as something that is useful in and of itself. So think about it this way: as x is very, very small, the sine function essentially becomes the same as the function x. You can see that. You can even see that in here. Well, let's draw a plot of that. Here's the sine function, and here's the function f of x equals x. And when x is very, very small, the two functions are very similar to each other. Okay, so now I'm going to give you an example that uses that in a non-trivial way. Let's calculate the limit when, let's say, y goes to 0. Let's do x. When x goes to 0, of sine of 7x divided by x. It looks a lot like before, except that now we're doing it with 7x instead of x. So what do you think?
First of all, on way can use product rule.
Here's a product rule. Maybe, but so I hear a suggestion in the front to use the product rule, but we're not, in principle, we're not calculating a derivative. Right now, we're just calculating a limit. So if you wanted to use the product rule, you're welcome to. It's a nice idea, but you first have to rewrite it so that it becomes a derivative of something. Right now, it's not a derivative of anything. Okay? What do you think? Can I cancel the x here and the x here? No. Sine of 7 divided by 1? No, right? Why is that? That's because it's sine of 7x, right? If it was sine of 7 times x, I could cancel out the x, no problem. But that doesn't work. So then what? Multiply by 7. Multiply, here in the front, multiply by 7 what? Yes? You're talking about L'Hopital's rule, right? Correct. Yes, we don't know L'Hopital's rule yet, but that's a good point. And when you know L'Hopital's rule, we can do that too. Yes. That's right. Why do you suggest that?
Because sine 7x over 7x is equal to 1.
Exactly. So what you're suggesting is instead of dividing by x, let's try to divide by 7x. You see this expression here, 7x, is not the same as what's down here. If we got it to be the same up and down, right? If this was a 7x, then we can argue, and this is what we're going to do now, we're going to multiply by 7 this thing, and then we can say, look, as this number 7x becomes smaller and smaller, sine of 7x divided by 7x becomes roughly equal to 1. But I cannot just go ahead and shamelessly write a 7 in there, which I just did. I have to undo it would be a mistake if I just do that. So I have to multiply by 7. I divide by 7 and I also multiply by 7. That's the trick. If you want to think about it in these terms, you can define a new variable, for example, theta. You can define theta to be equal to 7x. And this is the same thing as the limit when theta goes to 0 of 7 times sine of theta divided by theta. You see, since theta is just 7 times x, having x go to 0 is the same thing as having theta go to 0. Right? And this is converging towards 1, and the 7 is just 7. So the whole thing converges towards 7 times 1, which is 7. I find that surprising because this limit is supposed to converge to 1, but suddenly this slightly different thing converges to 7. Okay, so let's do another, a little bit harder example of the same thing. And that is the limit when x goes to 0 of sine of 2x divided by sine of 5x. So this is harder. Any ideas to how we can solve this? Okay, so once again we're going to somehow bring it similar to this limit over here, which we know is equal to 1. So I'm going to write this as the limit when x tends to 0 of the following large fraction. This is going to be sine of 2x divided by 2x. Once again, I'm shamelessly putting there what I would like there to be, divided by sine of 5x divided by 5x. And I know this thing converges to 1 and this thing converges to 1. And now that I shamelessly put there what I want there to be, I have to undo it. So I'm multiplying again by 2x. And here I'm going to multiply again by 5x. So now I'm good. I'm not changing the value of the limit. Do you agree? Okay, now what? We have something that becomes closer and closer to 1. This part becomes closer and closer to 1. This part becomes closer and closer to 1. And I'm actually at this point, I'm not even going to make the change of variables. I'm going to leave it as 2x and 5x. You see, whenever this expression is the same as this expression, whenever that expression goes to 0, whether it's x, theta, 2x, 5x, whatever, then that thing, the whole fraction converges to 1. Okay? And so this converges to 1, this converges to 1. What does the rest of this fraction converge to? Well, I can actually cancel out this x with this x. Now I can, right? And this top part goes to 1, this bottom part goes to 1, and this goes to 2, and this goes to 5. So the whole thing is equal to 2 over 5. And let's do one more, since we're doing the different types of this kind of limit. What is the limit when x goes to 0 of, let's see, sine of x squared divided by x? Exactly. So the principle has been the same all the time, which is you want to have the same thing in here as you have on the bottom. And right now we have an x. So we can multiply this by x and divided by x. That's right. Okay. And that we can break down into, if you will, into two limits. The limit when x goes to 0 of x multiplied by the limit when x goes to 0 of sine x squared divided by x squared. Now once again, if you want, you can make a theta equal to x squared if you feel better about that way of doing it. But you can think about simply making this expression very small. Whenever this value, x squared, becomes very, very small, then this goes to 1. Okay, so this is 1. And this goes to 0. So the whole thing goes to 0. Okay, do you have any questions? All right, we have something like 5 minutes left. So what I wanted to ask you is if you have any questions about the exam that you would like to know. Yes?
How are we going to store our scores? We're going to get it?
Okay, my TAs are still finishing up a part of the grading. I did a part of the grading, and they're doing part of the grading. We're going to add everything up, and hopefully by tomorrow during the discussion section, we'll give it back to you. Okay, that will be the plan. But
can we ask like specific problems?
yes.
I don't know if there was one on the blue test, but on the yellow test there was one where it was like you evaluate a limit, and then the next, like part B was like set the above limit as the derivative.
Okay, so I have a question about a specific problem in the exam. So for example, the limit when x goes to 3 of, I think it was this, it was square root of x plus 4 minus square root of 4 divided by x minus 3. Oh, sorry, x plus 1. Yeah, okay, something like that. So let's see, let's look at this expression. So, so if we wanted to solve this limit, the top part converges to 0 and the bottom part converges to 0. How does the top part converge to 0? Because when x becomes very, very close to 3, the square root of x plus 1 becomes very, very close to the square root of 4. And this is square root of 4, so the top converges to 0, and the bottom converges to 0. Okay? Now, I am actually not going to do this limit, calculate the limit itself, because we've done it many times. The way to do it is to multiply by the conjugate. So the conjugate of this expression here is square root of x plus 1 plus square root of 4, up and down, and then you multiply out, and that's it. But the more interesting question in the exam was to write this expression as the limit of some function in such a way that it becomes a derivative of the function at a point. So let's compare this with the limit when x tends to a of f of x minus f of a divided by x minus a. The question in the exam asks to compare this and to make it look like that for some function f and some point a. So if you look at these expressions, can you tell, for example, what a is in here? Just by looking at it? Well, this is the limit when x goes to 3, and this is the limit when x goes to a. So a better be equal to 3. Otherwise, this is never going to look like that. Right? So that's the first step, is to identify that a has to be equal to 3. Okay, second step. What function do we have to come up with so that square root of x plus 1 is square root of x? Sorry, it's f of x. And so that f of a, f of 3 in this case, is equal to square root of 4. Well, easy, right? If this expression is supposed to be f of x, then presumably f of x is square root of x plus 1. Okay? So if you set f of x equals to x plus 1, then this expression becomes exactly equal to that expression in there. Okay? And once you do that, then this is equal to f prime of 3. That's that. That's how to solve that problem. Okay? Okay, we ran out of time. So see you Wednesday.